Hello, everyone. I'm Gauthier Thieren with intoPIX, and I'm going to give a presentation about the different IPMX video profiles and specifically more on the codec choices that you have with IPMX. So as Jed explained in the previous presentation, IPMX aims at covering a wide range of use cases. So of course, you've got more professional production with, for example, camera or production switchers. So typically, what's covered right now with the SMT2110 protocols. But of course, you've got many other kinds of use cases that cover a wide range of devices. And those devices each have, let's say, their constraint. And that means that IPMX, to be able to be implemented in each of these devices, have to support different kinds of technologies, especially at the codec level. So that's what I'm going to talk more about in this presentation. So video is really the limiting factor in AV over IP. IPMX has many different specifications and protocols underneath, really. So you've got, of course, routing and control with NMOS, as Jed explained in the previous presentation. You've got audio, you've got security and encryption, you've got KVM capabilities with USB over IP, and of course, you've got video. But video really stands out compared to the other aspects of the IPMX specification, namely that it's hard to have a one-size-fits-all solution. With all of the above, you can more or less reach the objective that you want to obtain with a single solution. Well, with video, the hard part is that all of those devices that I've shown before don't necessarily have the capability to handle a huge amount of data, and therefore it makes it prohibitive in a lot of use cases. And therefore, the solution to this problem is to compress the data. For example, you want to make sure that you get into devices that have interfaces below 100 megabits per second. That means that you've got to go for a codec that compresses a lot. So this means that depending on the device and the use case, you've got to have different codec options. But the big question is, how do you select the codec? What are the different options that exist? So I want to first give a quick explanation of what is actually a codec. So the basic idea of a codec is that you take data in, you look for redundancies, you remove those redundancies, and then you send the data. On the other side, you've got to decompress the data, restore the original format, and then you can actually view the content. And so there are several stages in that process. The first is really about finding correlations, so looking for redundancies. And that part is completely lossless, mathematically lossless. So if you've got 2 times the same pixel right next to each other, of course, you only have to send it once. That's the basic idea. The second step is the quantization phase. And that phase is really, that part is lossy. So you determine how much of the data is actually useful. So you will arbitrate based on several criteria. And the most important one is, okay, how much of that data is actually useful for the human eye? If you're working, for example, with machine vision, that decision is different because machines look for other kind of data than the human eye. And then the last stage typically is entropy coding, where you assign variable bit lengths to different type of data. So if some of the data is very frequent, for example, you will assign a very short bit length, because then that means that you will transmit less data. If something is very not common, then you will assign a longer bit length, because that won't take too much space. And the real question is, what's the extent to which you look for redundancy? What's the compression granularity? Are you looking at part of a frame? Are you looking at an entire frame? Are you looking at several frames? And that's really the crux of what a codec does. So there's a trade-off that exists. You can wait for longer, typically, to have more data, so you can look for more redundancies and you can compress more. But what this means in practice is that since you have to wait more, you also add more latencies. And in some use cases, that can pose a problem. So that's why within IPMX, there was a careful selection process of codec that took place, where several criteria were looked at. So, of course, you can send the data in an uncompressed fashion. So that's really that's the most straightforward way of doing so. So you take one pixel in, you send it over the network, and then you receive it on the other side. So all of the information is self-contained in a single pixel. And of course, in that situation, you don't add any latency, except network latency, processing latency, but no latency related to compression. The second approach is to look for redundancies within a certain number of lines. What that means is that when you start receiving pixels, you don't have to wait for the whole frame. You can wait for a few lines, and then you look for redundancies within that number of lines. And that means that you maintain very low latency, because if you're looking for, I don't know, 10 lines, for example, you would be under 100 microsecond of waiting time. That means that you can start sending data over the network while the rest of the image hasn't been processed yet. And that's how a codec like JPEG XS works. The second option, which is also frame-based or subframe-based, is to use a temporal coding. So the basic idea here is if you've got some static content, so content that doesn't move from one frame to the other, instead of sending the whole data again, you can only send the difference. And that means that you can compress further. And that doesn't mean that you need to add latency, because you can work at subframe granularity as well. So, for example, the TDC profile of JPEG XS works that way. So you only send the difference per set of lines, and therefore you don't add any latency compared to the standard JPEG XS profile. And then finally, you've got the HEVC, HEVC kind of codec, so long GOP codec. Those codecs typically look at redundancies across several frames. So you would buffer several frames at the encode and at decode and look for redundancies, temporal redundancies between those frames. And that adds latency, because you need to wait for a few frames typically to start encoding and sending the data over the network. And then on the other side, you need to wait for a few of those compressed frames to arrive to start decoding. So that's really the trade-off that you're facing. So the more you wait, the more you can look at data. So the more you can find redundancies and the more you can compress. But of course, the more you wait, the more latency you add, and that can pose problem in some use cases. So to answer all of those needs, IPMX has defined 4 video profiles that serve the basis of interoperability. So the technical recommendation documents, so the VSF TR-10 documents, don't specify a specific codec in the same way that SMPTE 2110 with its -22 specification doesn't mandate a specific codec. But interoperability the standard is about interoperability in practice, not in theory. So that's why AIMS, which is more the marketing arm of the IPMX initiative, has defined 4 video profiles and selected 4 codecs. 3 codecs and the uncompressed video profile. And crucially, all of those codecs are standardized either at MPEG or JPEG. So these codecs are future-proof in the sense that the specification are open and anyone can start implementing it. The IPMX allows for proprietary codec, but to be IPMX compliant, to be IPMX certified, you've got to support at least one of those profiles. And so that includes the video profile and or the audio profile. So the 4 video profiles that exist are the uncompressed video profile, which is compatible with SMPTE 2110 if some, let's say, additional constraints are put in particular related to timing and synchronization, PTP. And then the JPEG XS profile is typically compatible with SMPTE 2110-22 equipment that uses JPEG XS with the TR-8 specification. And then you've got 2 long GOP codecs, HEVC and H.264, as well as an audio profile. And then on top of that, AIMS has defined profile options, which are let's say, additional features for a specific video profile. So you've got the TDC, so the temporal differential coding for JPEG XS, which adds additional quality for the static content, so desktop type of content that I've explained. And then you've got the HEVC option for the main 444 10-bit profile. So that's more for AV type of application where you need that 444 quality. So I want to go quickly into the different video profiles that exist and what are the trade-offs that you observe with those video profiles and for which use cases it's advisable to use them. So of course, the uncompressed video profile, there's no visual loss in quality. You just process the pixel as is. So that means that you've got very high quality, the highest quality you can get, and very low latency. It's also pretty low complexity in the sense that you don't have to process the data to actually send it over the network. Also, this enables frame-by-frame access because all of the data is self-contained, not within frame, not within part of frame, but within pixel even. And a typical use case is if you want to do professional LAN production. So if you want to be compatible with 702110-20 production equipment, or if you want to interface, for example, with a broadcaster studio. It can also be used in the AV distribution use cases where you don't have bandwidth constraints. The second profile, so the JPEG XS profile, is great if you want to have that uncompressed quality, but where you don't have the available bandwidth. So it's really designed to replace the uncompressed video profile in those bandwidth constrained use cases. And of course, you still maintain the frame-by-frame access that the uncompressed video profile offers. So it's great if you've got mixed storage and live video use cases. And it's also visually lossless, even after several encoding or decoding cycles. So the way the codec was designed is that it allows for the criteria was, okay, we should do 7 encoding and decoding cycles before we can see any any decrease in quality. So it's a great profile if you want to do some professional production that is compatible with 702110-22. So that can include studio production or contribution links between sites, or if you want to use some high-end cloud-based workflows. Can also be used in post-production workflows where you need to store JPEG XS frames or play them back. And of course, it's highly suitable for any kind of distribution use cases where you need to maintain very low latency. So typically image magnification. Then I want to quickly explain a bit more the TDC profile of JPEG XS and how it differs in the use case. This profile mode was really designed and conceived to enable 4K 60 content transport over 1 gig networks. So it has the same latency as the JPEG XS typical profile, but adds on average a 50% improvement in compression ratio. And so that's great for video distribution in office environments where you've got, for example, a desktop type of content where the fact that you've got some temporal coding, it means that quality will build up over time. And so if the content stays static, so think of an Excel spreadsheet, a PowerPoint presentation, that content mostly stays static over time. And so quality will build up over time and reach close to uncompressed level after several frames. Then you've got the HEVC video profile, which is great if you want to maximize the compression ratio. It's the codec that offers the greatest compression ratio, really. The trade-off that you have to make depends on the profile, but usually you've got to make a trade-off on the latency, but also the algorithmic complexity. So you've got to use dedicated chips to do encoding and decoding. It's practically impossible to do it in software. And it's great if you want to work with bandwidth constrained workflows. So, for example, if you want to embed IPMX into displays, where displays have typically 100 megabits NIC capabilities, and so that kind of limits it to those kinds of long GOP codec. It's also great in non-latency critical AV distribution use cases. So that can be a media player distributing video to a facility, for example. And also, it's also a good profile if you want to ingest into unified communication devices, because those devices typically use chipsets that have HEVC capabilities. And then you also have the H.264 video profile. The use case is more or less the same as HEVC, but the reason why it was included is because H.264 is pretty much the lingua franca codec on any kind of SoC platform. So it's basically everywhere out there. And so it's easy to transform any kind of device into an IPMX compatible software, an IPMX compatible sender or receiver. And so this makes make H.264 the only viable option in those devices. So how do you use the different codec and the codecs in practice? The answer is pretty simple. It depends on what use case you're trying to achieve. So it depends on what bandwidth you've got available, what kind of latency you want to achieve, and what kind of quality you want to achieve. So in practice, if you want the highest quality, the lowest latency, of course, you will go for the uncompressed video profile. So that's what you see on the left side. So if you do some 2110 production, you would go for this profile. And then if you need to distribute that video in a corporate AV LAN environment where latency is critical, you could use, for example, the standard JPEG XS profile, JPEG XS height for cameras, and so send those feeds back to your 2110 equipment, for example. And you could use the temporal differential coding mode of JPEG XS for a LAN AV distribution where you're constrained by your 1 gig network and where you want to send 4060 content while maintaining very low latency. And then on the second scenario, where you have a more bandwidth constrained environment and where latency is less critical, you might also have a mixed use of codecs. So if you've got a small production setup, for example, where bandwidth is constrained but latency is critical, JPEG XS will also be a good option there. But then if you've got some AV distribution using a digital signage player that just plays back content, you don't need that low latency. And that's where a codec like AVC or HEVC are good options. So how do we guarantee profile compliance? Well, there was in January the first IPMX certification event I attended. So there were 3 media profiles that were certified, and that means that all of the devices that support those media profiles are compatible with each other. And there is an upcoming certification of additional profiles and profile modes. And this was carried out in the EBU, so the European Broadcast Union facility. So that was great because we had a common network environment that eliminates any kind of variables we could observe. And also we had that was an independent organization that is outside of any companies that participates in the IPMX activities, but also outside of AIMS and VSM. So that was great to make sure that we had an independent oversee organization to make sure that we did things properly. So what this enabled, what the certification event enabled, is that the companies that were certified can now officially use an IPMX certification mark, and so this gives confidence to users, but also integrators, companies that have to do quotes. That can be a differentiating factor, saying, okay, I want devices that have been IPMX certified because I'm sure it's going to work in my facility. And that's also the reason why the profiles exist in the first place, because you want to make sure that when you select those devices, they are compatible with each other. And also this certification event, with this certification event came an official IPMX registry that lists all of the devices that are compatible with the IPMX standard. Overall, more than 50 devices were certified, and that includes a wide range of devices. So that included software solutions, but also switchers, LED wall processors, KVM appliances, and HDMI or SDI gateways. Say that again? So not yet cameras. We expect this to come in the near future. But there are already some 2110 cameras, either with JPEG XS or the uncompressed video profile. So those cameras are compatible already, because as part of the IPMX specification, you've got to be able to support 2110 products. So IPMX receivers have to be able to decode 2110 senders. The other way around is not true, but since cameras are only senders, there are already IPMX compatible cameras out there, basically. So I've talked about the IPMX certification, but how are IPMX profiles used in practice? Well, from what we observe is that 2026 seems to be the year for IPMX because this is, as Jed already mentioned, we've seen the first large-scale IPMX deployments to take place, and that includes installations in the hundreds up to the thousands of endpoints. And so that can be in corporate environment, but also for public institutions. So typically companies that have mixed needs for both broadcast facilities, but also Pro-AV facilities. And so what we observe is right now still those companies are mostly companies that have a large budget that want to really be future-proof. But we expect that these installations would be more and more cost-effective as IPMX becomes more widely available. And what we observe as well is that there's a growing interest in other communities as well. For example, in the broadcast industry, the fact that it's software-friendly and compatible with SENTI 2110 makes it highly suitable. For example, for KDM application, where it's mostly proprietary right now. So that's it. If you have any question, feel free to ask.